Hello, everyone, here in the studio, in the classroom, and out in cyberspace. Today's lecture is entitled Conflict and Tolerance. Before we get into the exact meaning of what that is, as you will see, I will devote the first portion of the lecture to some words. So I'm going to devote a few words about Peter Hammer in the context of my beginning and some of the work on graph theory that he did that inspires some of us who are working in algorithmic graph theory. So here's a picture taken about 10, no, maybe 15 years ago when Peter Hammer, who's right here, visited us at our institute. And there's no conflict there, only tolerance. Some of you might recognize in the picture Irit Hartman, who spent a couple of years in Bangalore recently, and Juri Turan, that's me, and my wife Lynn. So let me say a few things about the contributions of Peter Hammer to algorithmic graph theory. Peter authored more than 240 research papers over his whole career. 20% of them were in graph theory, and that alone would be a significant number just for an individual, just that 20%. Together with colleagues, he worked introducing families of graphs like threshold graphs and split graphs. He invented or promoted different parameters in graphs, like the Dilworth number, the splittance of a graph, and a technique called destruction. And so I would like to begin by mentioning some of his fundamental contributions. Here's a picture of him when he visited us. He gave a series of lectures, and this is the president of the University of Haifa at the time. So conflict and tolerance in graphs. What do I mean by that? It's a natural extension to ideas that we've seen in families of intersection graphs. In fact, intersection is the epitome of conflict. When you have objects that intersect, they conflict with each other. Now, such objects, as we've seen in the course, in our studies, could be intersecting intervals on the line, circular disks, live areas of variables in flow digraphs, or any number of other different sets. One of the influences of my studying in graph theory and algorithmic graph theory started when I read the book by Claude Berge, Graphs and Hypergraphs. His publication in this book in 1970 was a spurt that drove a lot of people into looking at new ideas in this area. And in that book, you have comparability graphs, chordal graphs, interval graphs, and some other intersection graphs. So in that first generation, you might say, these were the classes of fundamental interest, which we studied at the beginning of the course. There's sort of a hierarchy, and you recall that we have comparability graphs and chordal graphs, and then the interval graphs were characterized as those where the graph is chordal and co-comparability. Permutation were characterized as comparability and co-comparability. And so you might ask, well, there's something missing. What would be chordal and complement chordal? And that answer is the class of split graphs. And this was discovered and published in a paper by Foldes and Hammer. Foldes was a student of Hammer at the time. So let me tell you what a split graph is. A split graph is a graph whose vertices can be partitioned into independent set and a clique, as you have here on this a clique, and some edges going back and forth any way you like to connect them. And their characterization of this class was that this is a split graph if and only if the graph, not sure what's happening with the slides, but we'll go back to the slides, please, if we can. So it's a split graph if and only if the graph and its complement are chordal, if and only if it has no forbidden subgraph as listed here on the slide. No 2K2, no C4, and no C5. Now this is a very nice mathematical characterization, and it feels good because we finished that hierarchy and we have a forbidden subgraph characterization. But you might want to know about recognizing them without having to like check to see if it has those forbidden configurations. And here is a very beautiful aspect of this class of graphs. If you order the vertices by their degree, decreasing, so vertex 1 has the largest degree, then comes vertex 2, and so on. These degrees, as they form a decreasing sequence, you could see as sort of going down from high to low. On the other hand, the index I, starting at 1, goes up. At some point, they cross. And at that crossing point, we'll call that M. So let M be the maximum index where di is greater than or equal to I minus 1. So that's the place where these two curves cross. That number M is significant. So significant that it allows you to characterize split graphs. So a graph is a split graph if and only if summing the degrees from 1 to M equals M times M minus 1 plus the sum of the degrees starting at M plus 1 going up to N. So you can think of it as what is the sum of the degrees? Well, it would be this area below and this area above. And so it's saying that this area, if we were to draw like a rectangle here, an M by M minus 1 rectangle, this area plus this plus the area on over here adds up to this total area over here. Okay, why is this interesting? Well, first of all, it's a nice equation, but it allows us to recognize split graphs in n log n time. Why? We can just sort these degrees and then find the place where I meets the curve, just with a linear search. And so determining that M allows us to then calculate this formula. Either it works or it doesn't. So this is one of the few classes of graphs that you can recognize in n log n time. You only have to look at the edges because of this characterization. It can be recognized just by its degree sequence. They went on to define the splittance of a graph, any old graph, any general graph, which would be the minimum number of edges that need to be added or erased in order to make G into a split graph. It's a kind of graph editing problem. And their theorem of Hammer and Simeone, who was also a doctoral student of Peter Hammer, is that the splittance depends only on the degree sequence. And it equals this number. So you'll recognize these terms again. And if you take that and take half of it, you get that the splittance depends only on whether or not this is satisfied. Okay, so this is one of the few classes where editing can be done in polynomial time. Now let's move on to another invention of his called struction. This was a method for computing the stability number, the size of the maximum independent set. And in some work in 1984, he proposed and showed that if you, a kind of transformation of the graph, where you transform the graph in a certain way, And by doing that, you will have reduced the stability number at each step. So you do this transformation, then you do it again and again, and each iteration you've lowered the stability number by each step until you've basically got something that is trivial to look at. And then you just add the number of iterations. This was useful to give the first polynomial time algorithms for a few different families of graphs. Whoops. This is a kind of example. And all this is supposed to represent is that you take a vertex, you look at its neighborhood, and you do a kind of replacement and fill in some edges here. And although this could have exponential growth, for some classes, that growth tends to be not exponential, and then you get a polynomial time algorithm. Another idea that is very trivial that any of you could understand and see for yourself is that if you have a situation like this in any graph where the neighborhood of x is contained in the neighborhood of y, closed neighborhood, then if you were to delete y, the independence number, the size of the largest independent set, would remain unchanged. No change in the stability number. Why is that? Because any stable set would contain either x or y, or neither, but never both. And any stable set that contained y could be replaced by kicking y out and sticking x in. It has fewer neighbors, so you would never have any problem doing that. So one can always neighborhood reduce a graph and maintain the stability number. And that led us to look at what we could use that for in some classes of graphs. And it turned out that on circular arc graphs, you could perform neighborhood reduction and bring the graph to a certain canonical form. And that canonical form was easy to read off what the stability number would be. So this was a very greedy kind of algorithm just by doing neighborhood reduction. And that gave it the best algorithm for stability number for circular arc graphs. Here's something else that inspired some new work. They had a paper that looked at a problem that came from electrical engineering. Look at the diagram here on the top. You have some sort of set of small chips on the top and on the bottom, row 1 and row 2, and they have to be connected through various terminals. And so you are given the kind of input almost set where you know what chips have to be used, what order they are, and what terminals have to be connected to each other. That's your input. But you can do something to try to optimize this, and that was you are allowed to flip any cell that you like, lift it up, turn it over. I mean, you wouldn't actually turn it over. In the design, you would decide whether it would be heads or tails. And sometimes if you flip some of them, you will reduce the number of rows in this channel. So in the original, you can see I have 1, 2, 3, 4, 5 different rows. By flipping this guy, it reduces it down to 4 rows. And that helps you to have less area for your chip. The same logic, you just flip it and then adjust your connections. And sometimes you're lucky. The idea was, what collection of flips should you do in order to minimize that width of that channel? Okay, that came as a kind of inspiration to say, let's try to do something like that for permutation diagrams, which we've seen when we studied permutation graphs. So suppose you have a permutation diagram where the numbers on top are blocked into segments, and the bottom is also blocked into segments. And let's say this is a totally theoretical question, but it is inspired and maybe has something to do with what we just saw. You're allowed to keep any segment as it is or reverse its order. Just flip it. When you reverse its order, of course, some of these crossings stop being crossings, and some of them outside between cells remain crossing. So the question would be, how can you select which cells to flip in order to minimize the thickness of this diagram? That is really the maximum cardinality of a clique. So can you choose a set of flippings so that omega of the graph, the clique number, goes down? Well, so we investigated that question and came up with a polynomial time algorithm to find an optimal flipping for permutation diagrams. This is a kind of problem that you might explore if you wanted to do a project in this course. You could read that paper, present it in a class, and so forth. It's one of those journeys that you can take on your own based on what you've learned in the class. Now let's look at the class of threshold graphs, which is probably the most important family of graphs that Peter introduced. So a graph will be called a threshold graph if there exist positive weights on the vertices and a threshold that's positive, such that you can distinguish between independent sets and non-independent sets by a linear combination of those weights. Specifically, S will be a stable set if and only if summing the weights on S will be below the threshold. And if you sum the weights and you get a number that is beyond the threshold, it is not a stable set. So if you can think of many directions, this is sort of like a hyperplane that cuts across n space. And the characteristic vectors for a stable set will be below the hyperplane, and the characteristic vectors for the non-stable sets will be above it. And here is the theorem that Hvatal and Hammer proved in 1977, or published in 77. A graph is threshold graph if and only if its complement is a threshold graph, if and only if there's a different weighting and a different threshold such that you can distinguish between edges by looking at the sum of their weight. Instead of summing everything on a stable set, you can also get a different weighting to distinguish adjacency or not, depending on adding the weights and comparing it to a threshold. The fourth and fifth I'm going to show you in reverse order. The fifth is a forbidden subgraph characterization, very nice structurally. But it's the fourth that is very interesting algorithmically. Repeatedly remove either a vertex that is universal, that means one that is adjacent to everyone, or an isolated vertex. And if you carry out this procedure over and over, it will result eventually in the empty set. So you have a kind of algorithm here where you take a graph, and on one side you have the Pac-Man that's eating universal vertices. And on the other side, the Pac-Man that's eating isolated. And they keep eating, okay, and when they meet and everything is out, then the graph is threshold. So you have them universal, isolated, 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 universal. If you can destroy everything, you have a threshold graph. Okay. So when I looked at Berge's book and studied it when I was in my graduate studies, he has one chapter on perfect graphs, and in that a section on comparability graphs and a section on interval graphs and a section on chordal graphs. And I got very interested. And 10 years later, I published my first book on algorithmic graph theory and perfect graphs, where I sort of expanded this whole idea from one chapter into a whole book. A lot of progress was made in those 10 years. In that book, there's a chapter on threshold graphs, Peter's. And it took another 15 years till there was another book written by Mahadev and Peled on all these different aspects of threshold graphs and related topics. So that sort of shows you how algorithmic graph theory was booming, and it continues to boom. I call the things here like the first generation and then the second generation. Mahadev and Peled were both also doctoral students of Peter Hammer. So now I'll tell you a little story, my encounter with threshold graphs. From New York to Kalamazoo to Keste. So I was at the time teaching at New York University, and I heard a lecture from two computer scientists from Stony Brook who were looking at a resource allocation problem. It's actually like PV semaphores for an operating system. And abstractly, you have T units available of some commodity. You have an agent who requests A sub I units of that commodity, and it's either all or nothing. You either get it satisfied or you don't. Okay? And a subset of requests that are satisfiable form a stable set in some kind of graph. What kind of graph? So they worked very hard to find a kind of graph that would meet their needs, and they even had a characterization for it, and it turned out to be the same definition as threshold graphs. Of course, they didn't know it. Neither party knew about the other, and I didn't know about Peter or Fatal either. So I worked on this problem a bit, and I got some results, and I put together an abstract, and I sent it off to a conference that I would be going to in Keste, which is in Hungary. But before I got a chance to go abroad, I stopped off at a different conference a couple months, I think a month and a half earlier, in Kalamazoo, Michigan. And there I saw Berge, who I had already met a number of times. And I asked him, well, did you ever see this kind of definition before? And he said, oh yeah, they're threshold graphs. Go ask Fatal. So I went over to Vashik Fatal and I said, Berge told me to show you this definition of something that I just found out about and I've been working on. And he said, oh yeah, that's what Peter and I have been working on in threshold graphs. So I said, how is it that I thought to call them threshold graphs and you have already been calling them threshold graphs? And he said, well, who knows? Maybe it was just so natural. Anyhow, fortunately, the result that I had was not subsumed by either of those papers. It was another result, and I will tell you what that result was. So in 1976, at this conference in Keste, when the United States of America was celebrating its 200th anniversary with fireworks and a big flotilla going down the Hudson River that I missed because I was in Hungary and not in New York City. And at the same time, the Israeli Air Force had a rescue mission in Entebbe in Ethiopia when an Air France aircraft had been Uganda. Had been hijacked, and it was the same weekend. I think that this theorem, though, outweighs both of those events. So a threshold graph, in my characterization, is a permutation graph. And what kind of permutation graph? permutation graph of permutations that can be formed of this form, a shuffle, what we call shuffle product. And the shuffle product means simply take the numbers up to k, take the other numbers from k plus 1 to n in reverse order, and then shuffle them in any way. So here is an example. You could just take them and shuffle them. So the order of 1, 2, 3, 4, 5 remains, and this 9, 8, 7, 6 remains, but you can shuffle them in any fashion that you like. And those are exactly the permutations that correspond to threshold graphs. Not the greatest, not the biggest idea in the world, but I thought it was very nice. So here's a picture of Peter in the 1970s in Waterloo, and Marty in, look about the same, right? In New York. Well, by 1983, Peter had moved on to Rutgers to found the Institute Rutgers. I moved to Haifa, where I was working at IBM, and then at Bar Ilan, and then University of Haifa. Peter gave me my first break, so to speak, into the journal world. He asked me if I would be the guest editor of a special issue of Discrete Mathematics, and then that went well, pretty well. And so then he asked me to join the editorial board of a new journal he was forming at the time, Discrete Applied Math, and the rest is history. He was a great enabler. He also gave me a second break about 7 years later, when he had the idea that there should be a journal that mixed mathematics and artificial intelligence. There was no good outlet for papers in there. And so he suggested we found a journal like this and that I be the head of it. And that's what happened, and it's been going on for 25 years. So those were ideas born at Rutgers, and other research ideas were also born. One time I was visiting there, and Ron Shamir was also visiting there, and we were working together. What should we talk about? We talked about some biology problems that he was interested, some temporal reasoning problems that I was interested, and we came up with the paradigm for graph sandwich problems. And that's what we worked on, and then went on to study graph sandwich problems of different families. So that was also born at Rutgers because Peter had invited us to come. So about that time also, the early 80s, when just before I moved to Israel, when I was working at Bell Labs, I had another discussion, not just the EPT discussion with John Klinsiewicz that we talked about yesterday, another discussion with Clyde Monma. And he was interested in scheduling problems, and he asked some questions about interference of time intervals, where perhaps you were a little bit flexible on the interaction of these intervals. That is, you weren't going to be too strict about real intersection, but you don't want them to intersect too much. It's like, I really don't care if the pizza is delivered at 7 o'clock exactly, or if it comes at 7:02 or 7:08. But if it's not there by 7:30, my grandchildren will be up the wall, and their grandfather will be up the wall, and we will not be very happy. Okay? So there is some flexibility, okay, not to have conflict for small intersections, a little bit of tolerance, but not total tolerance. Well, now we have that modeled in a graph theory context. So we suggested, Clyde and I, to measure the size of the intersection of intervals and associate a tolerance to each interval such that two vertices representing intervals will be conflicting or will be joined if and only if the length of the intersection, the size of the intersection associated with those intervals, is at least the minimum of the two tolerances. In this formula, what does this mean? I put an edge between x and y if the size of the intersection of their of their intersection is larger than the minimum tolerance. Say x is less tolerant than y. And if it's an interference that bothers x because it's too big, and he shouts out, conflict. Okay? So it might be that x causes the edge, it might be that y causes the edge. Okay? But we have a limit to the amount of tolerance, but we do measure the size of the interval. So this is a very nice mathematical model, and it opened up a whole world of chaos. So here we have some conflict, the prototype being very strict intersection. And then there's tolerance, where the big guy and the little guy get along, okay? Okay, to a point. Now those interval tolerance graphs are a whole subject on its own. Anne Trenk and I wrote a whole book on that class and the related questions that we published about 10 years ago. And that we won't be able to talk about because it would take a whole another series of lectures. But it's a place where you could go and learn on your own, or perhaps I'll give some other lectures another time on tolerance graphs. Another hook is that if you look at the EPT graphs that we studied last time, so we have edge intersection graphs of paths in a tree. Notice this is a kind of tolerance too. There we tolerated vertex intersection, but we did not tolerate edge intersection. So that too is a kind of loosening of intersection, limited fashion, to give you a model that maybe reflects your actual problem, and then raises the question of what kinds of graphs are you and what kinds of things can you do with them. Color them, find cliques, and so on. Well, Jameson and his pal Mulder introduced a more general model for constant tolerance models for degree-bounded subtrees, and this I introduced a little bit yesterday too, the HST model, where you have a host tree where the max degree of the host is h, the max degree of the subset that you're looking at, like paths or subtrees, is s, and t would be the tolerance. How many vertices in common do they have to have in order for you to shout out edge? Similarly, a different model was proposed by Bubelnex and Deering called neighborhood subtree tolerance graphs, or nest graphs. While I won't define them, there is a chapter in the tolerance book on them. And during this period of time, more and more research was happening on unit proper interval representations, tolerance digraphs by tolerance, which is what led Anne and myself to decide to write the book. Well, is conflict really that bad? Good fences make good neighbors sometimes. Is tolerance always that good? Well, there's always going to be a balance between tolerance and conflict. And here is a model that does that. We'll call it phi tolerance. So in '88, Jameson and McMorris and Mulder proposed replacing the min function in our interval tolerance graphs by other functions, such as max or sum or an arbitrary phi. Take a look at what's in the box here. It looks like that box that I had for interval tolerance. That is, you have an edge if and only if the size of the intersection of the two intervals is greater than or equal to some function phi of the tolerances. If this was min, I would have my class of interval tolerance graphs. But they also studied phi being max, sum, and also a special case where intervals are nested, called phi tolerance chain graphs. And there, notice they're doing something even more radical. They're saying that the size of the intersection in this case, if all of the intervals are stacked up like this, would be minimum of the two right-hand points. And so you didn't have to calculate this because all the intervals were of this form. Therefore, this became minimum of the right endpoints greater than or equal to phi of the tolerances. Now that sparked an idea of how to generalize that further. So Robert Jameson and I started looking at generalizing it further. And here is that model, which we call rank tolerance graphs. We'll give every vertex two parameters. One is called the rank, the other is the tolerance. The rank is its tendency to have an edge, and its tolerance is its tendency for not having an edge. And we defined a graph where x and y is an edge if and only if some ranking function of the ranks of the two vertices exceeds some tolerance function of the tolerances. So what you could appreciate about this is how it's gradually going from one model to a more general model to even a more general model. What these are, these functions, rho, the rank function, and the tolerance function would be, well, we tried different possibilities. And here are some of the results. Here is what this inequality looks like in symbols. xy is edge if and only if rho of the ranks exceeds phi of the tolerances. We call these phi rho tolerance graphs. Okay, so threshold graphs happen to fit into this paradigm. Okay, if you look at this boxed characterization number 3 that we saw before, well, this inequality that needs to be satisfied is of that form. Here, the W's are the ranks. The operation rho is sum. And the theta is a constant number. So it's just the constant function. All the tolerances can be equal and the constant function. So this shows that threshold graphs are certainly within this framework. Now, in their paper in 1988, they looked at this phi rho, although they didn't call it phi rho, they just looked at particular equations, inequalities, and showed that min-min were threshold graphs, min-max were exactly interval graphs, min-sum were exactly what are called threshold tolerance graphs, TT graphs, another topic that we won't cover on this visit, but you can delve into it on your own. Sum-min are the co-TT graphs, and phi-min were the phi tolerance chain graphs. Then Robert and I were able to show that max-max and sum-sum were also equal to threshold graphs. That surprised us. And then it started asking, well, what else is going on among these different functions? Here's a table to show what is known between phi and rho being these four, we could say, prototype common functions, and the classes of graphs that you get under the rank tolerance framework. Now notice on the diagonal, we have reflexive, that is, min-min, max-max, sum-sum, product-product. They always gave the threshold graphs. Well, we wondered, could that be generalized? Also notice the table is skew symmetric. That is, TT was above the diagonal, and co-TT was on the opposite side below the diagonal. Is that something that was just an anomaly, or could that be generalized? And there is also a question of strict versus non-strict. The definition as we gave it used a strict inequality, but you could replace that by a non-strict less than or equal to, and ask, are you getting the same graphs? Are you getting different graphs? And so, in general, this class of graphs is contained in this class. If at least one of the functions is continuous and weakly increasing, then those two classes are equal. And this happens to be the case for a lot of nice families of graphs, of functions. The skew symmetry also turned out to be a theorem. That phi rho is equal to the complement of rho phi. If at least one of these functions is continuous and weakly increasing, then you have the same complementary aspects for the non-strict inequalities. Then we looked at a whole bunch of other things, which I think I won't go into in detail, but whether functions have certain properties called like non-decreasing, weakly increasing, associative, and showed that if phi is weakly increasing, then phi is closed under the addition of universal and isolates and contains the threshold graphs. And so another set of conditions in which the class is exactly the threshold graphs. Okay. Now, I hope that I haven't lost you yet, but bear with me one more, a little bit more to tweak the functions that we're looking at and define something called a mix graph, or mix function. Mixed function and their rank tolerance graphs. So let theta be some number. Think of it as a fraction between 0 and 1. But not necessarily, but for right now, think of it that way. So if I mix, I have a mix function where I take my two numbers x and y, and I take 1 minus theta min contribution and theta max. So if theta was 0, this would disappear, and we would be talking min. If theta was 1, this would disappear, and we would be talking max. But all kinds of fractions in between. And average means theta half. Now, there was a paper that could be reinterpreted into this notation to say that if alpha was between 0 and 1, CoTT would be a subclass of mix alpha min. And the conjecture of whether this is strict or not strict is still an open question after so many years. Threshold graphs are mix 0 min, interval graphs are mix min, mix 1 min. So you could ask a question like, where is CoTT? Here's an alpha axis. Here is where alpha is 0. Here is where it's 1. As you slide across, CoTT happens to be right in the middle of it. Kind of amazing. We showed that CoTT is equal to sum min, mix half min, max sum, and a whole bunch of others. And we showed that if you look at mixing your mix, you have an alpha mix and a beta mix. Alpha for one side and beta for the other side. Then you got results something like this. The complements of mix alpha mix beta is equal to mix beta mix alpha. So that looks nice, right? And mix alpha mix beta is equal to mix 1 minus beta mix 1 minus alpha. Whoa. I could even plot that on a kind of diagram here. So here I have alpha increasing from 0 to 1, and then going off to infinity. Here I have beta going up from 0 to 1, off to infinity. This point is alpha 0, beta 0, and I get the threshold graphs. Over here I have alpha 1, beta 0, and I get the interval graphs. I slide across here. In the middle, I have CoTT. What's happening in the middle? You know, other places where it's like 2/3 across. We have no idea. Okay? And you get threshold on these 3 points, but those previous boxed equations, red and blue, what do they mean? It means that I have complementary symmetry on those diagonals and equivalence on the blue diagonal. So what else does that mean? It means that if you have some graphs here in a class A, well, then over here you have the same class A. Any graph that falls here also can fall here. And any graph that falls here, its complement goes over there. And what's happening out here in cyberspace beyond, we don't know, but we still have these complementary symmetries going on. And we have a few other results, like mixed theta is contained in split graphs. So split graphs are sort of on this line. There are other things on this line, not just split graphs. Below here would be a class that contains the unit interval graphs. Well, you can see there are a lot of questions that someone could write a whole PhD thesis on if you're interested. Or you could say, where is the spectrum of a graph? Where does it live? So where does P4 live? Well, P4 lives everywhere in this unit square, except on the threshold dots, right? Because P4 is not a threshold dot. So you can show that except for those dots, you got P4s running around like crazy. What about C4? Well, C4 lives in this upper triangle, but not on the diagonal because these are all split graphs. So you can't have any cycles there. So split graphs, so C4 lives here. You would never find a C4 in the, I mean, that's like, you would never go on that side. He only stays on this side. Where does C5 lives? Nowhere. Can't mix your alphas and beta anyway to get a C5. You'll never get a C5. Okay. So there could be some other wild and crazy ideas that you could think of how to have variations on the same theme. So I just throw these out as wild ideas. I have no idea whether you could find results or not, but why not? So here are some more ideas for conflict intolerance in graph theory. Consider a set of paths in a tree. Two vertices conflict if one of the two paths contains at least a quarter, 25%, of the other. Well, you could think of a reason why you wouldn't want them to overlap for more than 25%, but without quantifying it in terms of how many vertices, it's just percentage of how much they overlap. And here's the equation, the inequality. I can define it perfectly well. If the size of the intersection is greater than a quarter of the minimum of their length, you get an edge. What might this be? Is it conflict or is it collaboration? It's a matter of attitude. Associate with each vertex V a set of its members and a tolerance with each set so that you have an edge if and only if the union of the sets is less than the maximum of the tolerance. What is this? Example, disjoint sets of parliamentary members or political parties forming a coalition. Right? Form a coalition. But it has to be, the size of the coalition has to be below some numbers. X might choose his tolerance to be 3/2 of his size if it wants to dominate the partnership. And he might choose its own size if it wants to join anybody, like infinite tolerance. Right? meaning that if his tolerance is equal to his size, he doesn't affect this at all. He never causes an edge. Bring them all in. And so Trump would say, let's lower this even further. So you might talk about doing this for intervals, and you might talk about it for other functions. And what is all of this? Now let me just tell you the story of the professor and the mayonnaise jar. Once there was a professor in a philosophy class who, at the end of his talk, took from below his desk a jar and put it on the table. And then he took some golf balls and he put them in and filled up the jar with golf balls. And he asked the students, so is it full? And they said, yes, right up, golf balls up to the top. Then he took out some pebbles and he just poured them into the jar and they percolated their way until they got to the top. And he said, okay, is it full? And everyone said, yeah, it's full, right up to the top. And then he took some sand and he poured it into the jar and it percolated up and filled that empty space and then until it got to the top. And he says, okay, is it now full? And everyone said, yeah, it's full. And then he took 2 cups of coffee that he had and he poured them into the jar. Okay, didn't spill, just filled it up. So what does this all mean? So as a professor of philosophy, or maybe anybody that has a PhD, which is a doctor of philosophy, can say this. The golf balls are the important things. They're your family. They're your health. The things that you can't do without. The pebbles, those are also important, but not quite as important. Your job could change. Your home, it could change. You need all of those things. It helps fill your life and your existence. And then the sand is all those extra things that you fill up the extra time with. Going to the opera, performing in The Wizard of Oz, going to a football match, taking a trip to Indonesia. Those things that are nice to do, not required, but you find the time to it. And so you have to have those priorities in life of what is important and what is less important. If you were to put the sand in before the golf balls, you would be missing, you wouldn't be able to exist because you wouldn't have the important things. You have to know the priorities and the order in which to put the things in the jar. Then a student asked, so what was the coffee? And the professor looked and said, even after you filled the most important things, and the important things, and maybe the less important things, there's always room for a cup of coffee with your friends. Thank you very much, and we'll see you again somewhere, somehow, in the land of algorithmic graph theory.